since we will be using the same DG again, I borrowed this from one of you. So, just remember this DG, that is verifier filter. Okay, 3 coefficient filter. We are pretty familiar with this, so no need to explain this. Now, yesterday what I did, I was considering choice of the scheduling vector S. At that time, first I considered linear scheduling, and we said that if there is one edge between say IN to JN, then in the linear scheduling we assume the computation time here is, the scheduling here is S transpose IN, here S transpose JN. If this edge is EN, then schedule here must not precede the schedule of this. But then afterwards I also made it more realistic. I introduced computation time, because at S transpose IN computation starts here. Then you have to give the time was indicated by I think T subscript I. Then a propagation delay time, if you want, you can absorb, which is T com, I said T com. So this schedule must not precede the schedule of this plus Ti plus T com, that is S transpose JN S transpose IN plus Ti plus T com, and you can take this IN thing on this side. So, effectively you get in terms of the edge, and edge means the dependence graph is given by a few basic edges. So, therefore, I do not have to write the inequality for every all throughout the this thing, DG. So, essentially S transpose Ti plus T com. So, you get this kind of inequalities. That was for linear scheduling. I am repeating this for a specific reason, but then I considered another scheduling which was called affine scheduling, where I introduce, it is like instead of y equal to mx, which is perfectly linear, you add y equal to mx where c to that. So, y equal to mx plus c, which is not perfectly linear, it is affine actually, okay, where superposition is not valid. You know this, na? X plus c is not linear because superposition is not valid that way. It looks like a straight line, but it is actually looks linear. So, it is just that it is actually linear because of this S transpose edge being present there, but we need additional term. So, under affine scheduling, what we did was that schedule for IN was S transpose IN plus, what did I say, gamma I, isn't it? Gamma I. We introduced an offset as some constant. That is the schedule here, and the schedule for Jn was S transpose Jn plus some gamma j in general. In that case, we get the inequality that S transpose En should be greater than equal to, that is, this must not precede this plus Ti plus T com. So, that means gamma I minus, sorry, gamma j minus gamma I, that must not be. Okay. That time I gave you a reason for these gammas, that they add extra flexibility in the set of inequalities, because there is another fundamental thing in the choice of S, that S transpose D must not be equal to 0. Okay. This is also another inequality. Okay. Then I gave this. After that, I moved to another topic, and that appeared to be disconnected with this. That was algebraic description of a dependence graph. A dependence graph, I said, is actually infinite in size, but just algebraically you can through some expressions you can describe the DG in terms of few equations, and one of there is those that is called actually, I do not know why the name is given, but those equations, since it is iterative after all, because on the right hand side it might involve I comma j, left hand side I plus 1, j plus 1, or things like that. It involves iteration indices I and j. So, they call it, instead of equation, they call it iteration algorithm. It is actually called RIA. R for regular iterative algorithm, something like that, RIA. Do not bother about the names. Okay. So, RIA was what? That we consider each node. Okay, we consider each node, and we consider the RIA in the standard output form. Okay, in the standard output form. So, in the standard output form, we consider the output. There are 3 outputs here, one here, output on the left hand side of those equations, and there you manipulate the indices so that all of them have the same index, like I comma j, I comma j, I comma j, like W I comma j is equal to something, X I comma j is equal to something, and Y I comma j equal to something. That is what he said. That is called standard output form. That is, we go into this another topic, and these two topics are actually related, which I forgot to mention yesterday. That is what I will deliberate today actually. Why, what is happening, why suddenly RIA, and what is there is something inside. Okay, again, not clearly not given in the books at all. So, in its comes up it comes out of thinking. So, I will start with that. Why? What is the advantage? I said that there is an advantage of this business. Okay, what extra thing you get by this kind of treatment, that instead of starting with the DG directly, you get into RIA, then get a state diagram, and then on that finding out the edges and all, write the inequalities and all. This approach offers some extra advantage. That is what I will be, and that is not given in book at all. Okay, that is what I will be touching upon today first, and then I move to another, I mean, this 2D, another example of systolic array, which will be a 2D array from 3D to 2D transformation, that is matrix multiplication case. Okay. So, here what is RIA, for that DG only we said that if you consider I comma j, these are locations say I comma j. Okay. Then we said the RIA form will be what? Left hand side will be in terms of the output and right hand side input. So, we said if it is Wi comma j is Wi minus 1 j, right, I minus 1, j remains same. Similarly, x, if you call it xi comma j, xi comma j is I remains as it is, j minus 1, and y, you see ij, okay, was y I minus 1 j plus 1 plus I minus 1 j plus 1. So, here plus this into this. So, actually W I minus 1 comma j times x I j minus 1, but I know this is equal to this is equal to this. So, I fit that, I put that back here. Okay. So, these three equations. Then I drew a state diagram, which I am drawing down here only. This is a state diagram, okay, which is called RDG, reduced dependence graph. It is not infinite, it is finite thing, because it is coming out of this. One was for W, another for X, another for Y. Each variable defines a state actually. So, this means from W to W there is an edge, which is this edge actually. From here also you can make out it is going from I minus 1 to I. So, 1, and j to j means 0. Here also you can make out 1, 0 is coming like this. Similarly, from x to x, 0, 1 transpose after all in this direction. Okay. Here also you can see I remains I, but j minus 1 to 1. So, 0 and then 1, and y from I minus 1 j plus 1 it goes to I to j. That means, here there is a self loop h to itself, but that is 1 comma minus 1, right. So far it is repetition, but there is a reason. Soon you will see this why I am doing it. And from W I minus 1 j and I j. So, 1 sorry I j, this is that is why I did this. I j 0 0 0 0 transpose, that was the thing, right. And I mean, now you see what I am saying here. When I am considering DG only and then defining systolic array, I am not, if I am giving say affine, the way I have drawn to this node I will use only one gamma for this, to this one gamma, to this one gamma like that, okay, only one gamma. But if I get into this RDG kind of thing, then you can see what I can do. This RDG actually means this particular node, say, please see this, if you do not understand this particular node, I am generalizing as though I am drawing this node in a bigger way now, as though there is one processor which goes like this. Of course, it takes output y I comma j, fine, but along with that I draw a box as though this node I comma j, this itself, this entire thing is in a box. So, this entire box is in the coordinate I comma j, okay. And as though there is a separate line here, this was x, isn't it, and there is a small connection here, and there is another edge okay. This is for W just a minute, and this is for x I comma j, right. Now, this one, so there are actually three, please understand this. By expanding like this, I am able to show this by as though there are three processors. Of course, this does nothing, takes and gives. This also does nothing, takes and gives, but still I am showing it as some kind of node. And I can give different gamma to this guy, different gamma to this guy, and different gamma to this guy. So, if it is not affine scheduling, schedule of this will be what? S transpose coordinate vector. Coordinate vector I comma j, say, or whatever it is, in the general case I vector, S transpose I, here also S transpose I, here also S transpose I. But under affine, it will be something, it will be something, it will be something. S transpose I here, S transpose I here, I means capital I. S transpose capital I, S transpose capital I, but here some gamma 1, gamma 2, gamma 3. And if this is gamma 1, gamma 2, gamma 3, if gamma 2, gamma 1 are not same, that means there is a delay between them. Gamma 2 minus gamma 1 amount of delay here also. These things I cannot do in the plain DG form, because here this node I am just treating as it is. I am not getting into the separate parts like this is a separate line, this is a separate line and all that, no. As a result, if I have to use a gamma, I give only one, I am able to give only one gamma to this node. Okay. Is that clear, or I will be considering example? Is this clear? No? So, but as the example unfolds, you will see how this, you will understand it better. Okay. Now, in the choice of gamma, I tell you one thing. In the choice of gamma, this again will hit upon another box here. Okay, one particular edge. Similarly, this will hit upon another edge, another node here. Like that, okay. Now, in the choice of this gamma, I now make one more statement, that what is the schedule of this? S transpose coordinate vector plus some gamma, say gamma 2. What is the schedule of this? S transpose coordinate vector here plus another gamma. So, I am saying as far as this same line is concerned, you choose the same gamma. That is another condition not explicitly given in the book. Choice of gamma should be like this, which comes from the RDG. What I am saying is this: if this has got affine the threshold or whatever gamma or gamma 2 whatever, here also gamma 2, here also gamma 2, like that. Similarly, if this guy has got some gamma 1, this also, this processor also gamma 1, here also gamma 1, like that. Are you following me? This is an extra thing I am saying, extra condition on the choice of gamma, not given in the book, but this is what it is on the choice of gammas. Okay. So, here I tell you, suppose it is some gamma only. S transpose the coordinate plus gamma is the schedule here. Here also S transpose the coordinate vector for the same gamma. But if this is gamma prime, this gamma prime and gamma may not be same. What is the schedule here? S transpose same coordinate vector, but gamma prime. What is the schedule of this? S transpose same coordinate vector, but plus gamma. And obviously, gamma has to be greater than gamma prime, because arrow is pointing in this direction. Gamma has to be greater than or equal to, otherwise again that problem will come up. Okay. So, if you want to redraw your DFG so that each node is expanded, you put a kind of box and show this kind of edges and all that, fine. You do not need any RIA, you do not need any RDG and all that. But in a common DG, we only have dots. Okay, I am telling you, this is the problem with this, that here I have within one dot I have included everything. If you want to substitute this dot by a box like this in the DG itself everywhere, and this kind of connections are all, I have no problem with the DG. I do not need any RIA and any such thing. Okay, but that will make it look messy and all that. This is not DG. By definition, that is not DG. For that region only, I move to this kind of thing, where my target is this, that essentially there will be a separate line for X, separate line for W, and separate line for this Y, and within this only there will be local connections from W line to this processor, X line to this processor, and these nodes, these 3 nodes may have different schedules depending on the choice of gamma. This kind of arrangement under affine scheduling is not possible here, because here there is 1 dot means 1 gamma. But if I can expand this like this, separate lines and 3 different nodes within the same coordinate place in the same, then it is possible. But I do not want to draw the DG using this. But RIA helps me. RIA helps me because from RIA, if I draw the RDG now, what is the RDG? I have already drawn it. I am redrawing for your sake here again. You see, W to W there is an edge. Like this guy is going here. Is going here another box. Okay, so this W to W there is an edge, but I am telling you this node and this node, they will have the same gamma. Okay, same gamma. This is an extra condition I am saying, choice of gamma. This is not explicitly given in the book, but this is there. Your gamma is not arbitrary, there is some basic thing that has to be there. Now you see how nicely that is captured in your RDG thing. RDG from W to W, it shows there is an edge. That comes because of that RIA, those algebraic equations. I know there is an edge, that edge actually reflects this edge. From the diagram also you can make out there is an edge in the direction 1 to 0 from those RIA algebraic equations, so you can find out. Okay. Here also zero 1, I am just completing it, and x 1 minus 1, na? It was 1 minus 1, 1 minus 1 transpose, and this was now you see. Now suppose on this I want to write those scheduling inequalities. You see, from here what will I get? S transpose this edge, S transpose this edge 1 0. You remember the scheduling inequality under affine scheduling. S transpose H plus gamma j minus gamma I, gamma destination minus gamma source. That was the condition there. Here destination is W, source also W. Same, I said same gamma is to be there. That is the extra thing I said. So, gamma W minus gamma W. This must be greater than equal to propagation time plus computation time. Computation is nothing here, there is no computation. It is only a, in our example, it is only a branching node, it does not do any computation. Okay. So, something. Now, what something? I consider a specific problem in the book. It says, you consider this, that same DG everything, where T com is equal to how much? 1 unit time, T mult is equal to 5 unit time, and T add is equal to 2 unit time. Okay. So, now come to this, under this there is only T com here, because in this node, I know in this node there is no processing, no add, no mult in this. In this node there is no add, no mult, only computation time, only propagation time, that is 1. That is schedule here plus processing time plus propagation time, that must be less than schedule of the next guy. Okay. So, S transpose H plus gamma destination minus gamma source, which happens to be same, must be greater than equal to only T com, that is what I am saying, because there is no computation here. You are understanding this? You remember in general I said that S transpose J n minus S transpose I n, which is actually S transpose E n plus gamma destination, that is gamma j minus gamma I, that should be greater than equal to what? The computation required at ith node plus the propagation time T com. In this case, this does not require any computation, only propagation, only the propagation delay in this edge, which is captured by this edge. This edge in real DG is captured in the state diagram like this, propagation, but propagation time is there. So, that means this must be greater than equal to 1. Okay, this one equal, but gamma w minus gamma w cancels. Okay. Another inequality for this guy, S transpose plus again destination minus source gamma x minus gamma x greater than equal to just the propagation only, because it is also a branching node, no computation in this 1. Another inequality. Now, you see this edge, this is the beauty here. This edge, earlier it was not shown in the original DG, all these were put together into one dot. Now, there is an edge which is actually this edge. Okay. That edge will not have any propagation time, because that is local. I may showing the separate, but that is, I mean, almost one on other. So, will not have any propagation time. Okay. Just a minute. Yes, but we have to consider that edge, because S transpose, what is the edge? 0 0. As such, S transpose, obviously, I mean, under normal circumstances, schedule here and schedule here can coincide, because this is those shown separately, this is actually local. There is virtually no edge, they are almost touching each other, because on the same coordinate position only both the nodes are located. So, no propagation time, no processing time. So, these schedules could coincide, but I took that advantage or liberty to choose to define two affine thresholds here and here. Please see the thing. Here I choose, this is gamma y, sorry, I choose gamma y, and here gamma w. No processing here, no communication here, but still this inequality means something, because gamma I, y and gamma w, you have the liberty to choose them different. So, that means you can choose two different schedules, one for this, one for this, just in terms of the gamma. Okay, I said schedule here is S transpose times the coordinate vector, which is common for the entire box, plus some gamma, which is gamma w, and here the schedule is again S transpose times the same coordinate vector plus another gamma, that is gamma, what gamma? Gamma y. So, if gamma y or gamma w are not same, this in terms of you get, this gives 0, because edge is 0, they are local, but at least you still get this part. So, that means these two schedules are not same. So, if your gamma y and gamma w, you choose them not to be same, this much difference is to be there, means that much delay will come up in this path, similarly in this path. Okay. This is the extra advantage you have here, extra leverage you have here. You can choose different schedules even locally by just assigning different gammas. Understood? So, you see this inequality, if the gammas were not there, if it was linear, I would not have bothered. This has been all, the gamma thing does not exist. So, S transpose this edge, this is local, S transpose this edge is 0, because 0 0 vector, which means actually the two schedules can coincide, obviously, no propagation time, no processing time, it just takes and gives. So, fine. So, the processing here can start the very moment this gives it, they can coincide. and therefore this inequality would not have come. S transpose 0 0 greater than equal to 0 is already satisfied. This would not have been there. But under affine, I could assign still two different schedules by virtue of the gammas. I choose one gamma here, one gamma here. So, two gammas, that difference, that much of delay I have to insert here. I have that extra advantage here, you know. Okay. Similarly, for this also, S transpose 0 0 for this H plus again gamma y minus gamma x greater than or equal to, these are not given in books anywhere, you just write some equations. Okay. So, this H done, this H done, this H done, this H done, and final this one. This one I write where? I write here. S transpose 1 minus 1 plus again same H. So, same gamma down this line, same gamma, gamma y minus gamma y greater than or equal to 0. Okay. And then you to solve these inequalities. Sorry, no, it is not greater than or equal to 0, it is more than that. It is actually more than that. How much it will be? 8, very good. Because this age, this processing here can start only after processing plus communication, this propagation had taken place. Processing here means addition multiplication. So, 5 and 2 7 and then 1 8. Okay, so, this should be greater than or equal to 8. So, you get a set of inequalities, you solve them, you have plenty of choices. From here you find out S. So long, to give you examples, I gave you one, I started with the DG, then consider a particular P matrix which has a row vector there, and then depending on P I said okay, this is P, so obviously this is D, and once you choose D, I said okay, take S to be like this, so that S transpose D not equal to 0, and then we wrote the edges. Mapping, we found out that S transpose any edge is greater than or equal to 0 satisfied, fine. So, we went ahead. That is only for showing those examples to you. But in practice, you first start with not P, you start with S by solving the inequalities. Then you choose an S, so that you choose a D, so that S transpose D is not equal to 0. Then looking at D, try to construct a P, so that D is in the null space of that P. Okay. Here you can solve the inequalities, there are plenty of solutions possible. I come back to again after explaining all this, again I come back to linear case, that is all gammas are 0. So, I consider a special case of this, which happens to be linear scheduling, where all gammas are 0. If all gammas are 0, then what equations you get? Forget the gammas, as such this gamma does not matter here, whether even if they are present, gamma does not matter here, gamma does not matter, but they cancel, only here they are mattering, only these two cases, gamma y minus gamma w should be greater than or equal to 0, gamma y minus gamma x greater than or equal to 0, obviously because gamma here should be greater than this, gamma here should be greater than or equal to this, gamma here should be greater than or equal to this, and that much difference delay has to be put in, okay. But that is coming through these equations. Now, I am telling you again come back to the special case of all gamma 0, that is linear scheduling. Then these equations turn out to be what? S transpose 1 minus 1. So, if S vector has two components S1 and S2, if S is S1 S2, then this will give rise to what? S1 minus S2, okay. This will give rise to S1, gamma gamma cancels, this will give rise to S2, and these equations do not matter, gammas are 0 and this is obviously satisfied, okay, they do not come. So, out of these two equations, you say let us choose S2 equal to 1, S1 equal to 9, that is fine. After all, if you take higher value of this, this will amount to delay, more latency, because S is scheduling is related to delay. S times that age, if that is positive, that much of delay is there, is to be there. So, if S values are high, obviously number of delay goes up. So, never choose S to be say 100 or 1000 or things like that, it will be okay. Choose the minimum. So, I took 1 and therefore, I took 9. So, now my S is, so this is the systematic procedure. First, solve these inequalities, first dg, then RIA, then RdG. Then write the equations in general using affine, solve the inequalities. Once you solve, look for the minimum, that is which has the minimum coefficients. From that S, that is I now write down the S is what? 9 1 transpose. So then D, again there are plenty of choices of D should be such that S transpose D is not equal to 0, and again you do not choose too high coefficients of D because that is related to hardware utilization efficiency. So there are plenty of choices. I would have preferred 0 and 1 here. See, there are many choices, it cannot be 0 0 after all. Then one choice is 1 0. 1 0 means what is hardware utilization efficiency? S transpose D will be 9 into 1 9, 1 by 9, not much. If it is 0 1, 1 into 1 1, I would have preferred that, but maybe for example's sake he does not consider. So would have been better there. Another is you take 1 minus 1. If it is 1 minus 1, 8. Okay. 1 minus 1 or minus 1 1 does not matter because mod, you have to take the mod of that. So mod 8 or minus 8 does not matter. He takes, I do not know why, maybe for the sake of example he takes this. Once you choose D, so that S transpose D is not equal to 0, what is S transpose D? 8 HUE hardware utilization by 8, not much. Then find out P. P is in general, how to find out? P is in general in n minus 1 cross n matrix, in this case 1 cross 2 which is a row vector, but in general capital N minus 1 cross capital N matrix, and I said that design the matrix so that there is a square submatrix in that of size n minus 1 cross n minus 1 which is full rank. In that case the D will be nothing but a solution from the null space, and all other solutions will be just integral multiple of that. So here also I will construct P like that, but here it is pretty simple because it is only a row vector of size 2, because capital N for our case is 2, so n minus 1 is 1, so 1 cross 2. So it is very simple, you choose P so that P into D is 0, there is only one choice because it is 2 dimension, one vector, there can be only one another vector possible, so that the product is 0. So if it is 1 minus 1, that will be 1 1, in that case P D is 0. Okay. So if you do that, then we come back to our previous thing. We know we have already considered one example. Remember I drew through various colors, same P, same D. D is 1 minus 1 direction. So processors in these directions are clubbed into 1. These processors clubbed into 1, and then again I repeat this same thing. Only change will be because of the choice of S. That is, edge mapping will remain as it is. P, that is what I am saying, PE will remain same, but S transpose E will change because S has changed now, because of the 9 has come up and all that. So edges, what are the edges? Weight was what? 1 0 transpose, and then X input was 0 1 transpose, and your Y was 1 minus 1 transpose. So PE as before 1 1 0, but earlier S transpose E meant something, now it will be different because S vector has changed. 9 1, so it is 9, it is 1 and 8. Okay. With that, if you draw that thing, it is this. I will not draw it fully. Remember earlier there was only one delay flip flop. I was taking result in one cycle, another result another cycle, another in one cycle, coming back in the next cycle, that I was circulating. That thing is there also, but earlier I had 1 D, now I have 8 D. and then again circulate. That is it actually. Everything is same, only the delay amounts have changed. We have already done it earlier, remember, but that time there was no D here, it was only single D. Now, because of changed S, the delay amounts have changed, that is all. Okay. It is given in Paris book. Fine. So, now let us consider a matrix multiplication, because it was only no, it was only 2 dimensional. Yeah, please, questions are most welcome, please tell me. The internal working you try to understand yourself.
So what I'm saying is, sir, that so the 9D, so the input to it has been driven by, sir, two input lines, so like that wire.
Which were?
So where the loop is again coming back and joining the 9D. So the below one. So
Here, huh?
yes, sir. So that wire, so when it's entering the next 9D, it's being driven by two places. So like how is that coming?
Driven by two places?
Oh, okay.
I forgot the arrow. Okay. Everything is same. The delay figures have changed. They take care of that processing time by multiplier and add. That is why some more delay had to be there. Okay. Now consider a more interesting problem, because this FIR filtering problem I really would never go for this systolic business to draw the array, but now it will be very interesting. Now onwards, whenever I touch upon systolic array, there is time. Consider a matrix multiplication, a very benign case, 2 by 2 matrix multiplication. Okay, square matrix. We all know the results. C11 is A11 B11 plus A12 B21. I am not writing them, we all know. Suppose for the time being only these two matrices are given to you, you have to find out. But actually you are doing in real time. More and more matrices are coming in time, and you are going on doing multiplication, giving the output in time. Otherwise, why should I design an array? All algorithms are my real time algorithms. You are continuous stream of data coming, and I am generating continuous output. Okay, a discrete output, but regularly, continuously. So similarly, matrices are coming one after another. I will do the multiplication, I will generate the output. But for the time being, you assume that only two matrices are given. We'll do this. Now, what will be the DG firstly? Now, if you practice hard, you can draw the DG. It takes some time, but to minimize the time, I will draw the DG myself. I have the book also with me, though I know the DG because I learned the DG from the book only. But this kind of DG, again I told you, there is no systematic procedure of drawing DG. It comes from practice and all that. In this case, DG will be actually a cube. It is a 3-dimensional DG that will come up. Why 3-dimensional DG in this case? Consider, I forget about this 2 by 2 case. Consider a general matrix n cross n, n cross n, n cross n. Any result, any item, say I comma j, small I comma j item of the result matrix. How will you obtain that? I comma j, not 4, I comma j, that is in general I comma j, I and j are both from 1 to n, say. That is for I j 1 to n, 1 to n, I am writing this way, okay, 1 to n, MATLAB notation 1 to n. C I j will be what? A I k B k j. So, how many indices? 3. So, it will be 3 dimension. Okay. No, do not bring time now. Here there is no time. I am drawing the DG for this. There is no time here. Okay. 3 dimension obviously. These are not given in books. How many dimensions and everything. You see the equation and from there you can find out. Obviously, it will be 3 dimensional. And I would have loved to map it to 1 dimension, but I told you I will be going for n to n minus 1 transformation only, otherwise it is more complicated. Null space will have more dimension than 1 and all those problems will come up. So, I will be mapping it to 3 dimension to 2 dimension. Now, what is the 3-dimensional DG? It will be, you do not have to try hard now, I am drawing it for your sake, you just verify, it will be a cube actually. It is like this. I should have used different colors. Anyway, for the time being, it's okay, because I can complete it today. Oh, this dot I have to draw here. Forget this dot, this is here. This is not dot, this is all, my problem in drawing in real time. Real time means in the class. Drawing is always in real time, but Okay, and what other color? लगता है complete हो गया. अच्छा, here I give a, sorry, here 0, this thing A11, yeah, this thing I A11, A11, here A12, I think, yeah, A12, A22, A21. So, this matrix data enters here, and on these lines B11, then B12, B21, B22. What comes up here is C11, I think, yeah, C11 will come up according to me. Our claim is C21 will come up, C22 will come up, C12 will come up. You see, so nice it is. Start with here, just on this. These are all Mac processors. This into this, I am not showing them operation of the processor separately. I hope you understand. What this processor does, it has got 3 inputs. Everywhere this processor has 3 inputs, one coming from below, one coming from left, one coming from this. Okay. What it does, multiplies these 2 input, add with this, output comes up here, and this signal goes down this signal goes along. The same as the previous Mac processor, only the orientation of the lines are different. Okay. If that be, what comes out here? B11 into A11, A11 B11 plus 0, that comes up here. A11 B11 comes up here, and then A12 B21, that to that it gets added. So, that is C11. Similarly, A21, same B11 propagates, A21 into B11, A21 into B11 plus this 0, here is 0 here, plus 0. So, it will come up A2, you understand, A21 B11, and then B21 propagates. This is very important, you see, same B21 comes, same A22. So, A21 B11 done here, and then B21 A22. A22 is given here, but this B21 propagates. So, they multiply, add with that, so C21 comes up. You are giving new input, but same guy is coming here. Similarly, you are giving a new input A21, but same B11 coming up. C21 comes up, and now going this line, you are giving a new input B12, but same A11 going. So, A11 into B12 plus 0. So, what is that? A11 B12 plus 0. So, that remains, and then A12 you give this line, this propagates with B22, that comes up, and check with the last B12 you gave here and A21 both propagated, B12 A21, what is that? A21 B12 get added with 0, and then here again B22 propagated, A22 propagated, multiplied. Okay. It is not so easy, I mean, because things are common here, you see, it is forming a DG, it is not. So, that is why I am telling you, drawing DG is a very difficult thing. It is somewhat difficult, it comes through practice, smart thinking, it does not require maths background, smart thinking, looking at the structure of the problem. So, this is the DG. Okay. I define the axis also, this 3 dimension. So, I define my coordinate system I, j, k. This direction I will call I, this direction I will call j, vertical I will call k, I, j, k, this is my coordinate system. This is a 3D DG, I will be mapping it to 2D. So, what will be the size of my P, the P of P matrix, projection matrix? That will be 2 into 3. So, no longer a row vector. Life is not that easy as it was earlier, it is a matrix now. This is the reason why I have come to this. Those were very silly examples, you know, all vectors and all. This will be more, and this will really result in practical arrays. Each array will have, depending on the choice of P and all that. Here consider 6 arrays, okay, depending on 6 defined choice of P matrix and other things, and each has its own name, and they are used in practice. ICs are made using them. Okay, they really is in practice in IC form and all that. I will not consider all, I will consider 2. Okay. So, this is my IJK, and once again I will start with the same procedure of what? Converting this into a, through RIA, convert this into RDG, then bring in affine scheduling, write the set of inequalities in terms of S. Then I say that, look, for our specific problem, let us again come back to linear scheduling, so all gammas are 0. But you can happily bring in your gamma and okay, because otherwise what is the fun that I take you down the affine scheduling route and then finally say for the time being again forget affine scheduling and let us, but then that is how it is in the book, and at least you will go through the more flow actually. So, that means in this DG actually each node, this is a 3D, consider a I comma jth coordinate. In general here I comma j could be I is 1 to 2, j, I comma j comma k, sorry, I comma j comma k, I j k, both I is from 0 to 1, j is 0 to 1, k is 0 to 1, but suppose general I j k you consider, general I j k. Here this node actually ideally I should expand it in a box as I did for the 2D DG. There is one line for B. B signal, B goes down this line, and there is a node which is a branching node, it only connects this to this node, okay, because this information is needed by this processor, MAC processor. Similarly, there is another line for A, this A line, and there is another line for this result C. Okay. If I could redraw the DG in this expanded form, fine. I would not have required an RIA RDG business. I am repeating all those lines for your to avoid any possibility of confusion. Okay. That each node, because I will be going for affine scheduling and all those things to start with. Ideally, it should be like this, drawn like this, but DG is not that. DG, every processor is shown by a dot. So, if I introduce affine scheduling, I can give only one gamma to this, but here if I could redraw this like this, I could give 3 gammas, one for this node, one for this node, one for the main node. Okay. And by choosing 2 different gamma, I can introduce some delay also here. So, for that only it is better if I go for the algebraic description, that is RIA and RDG. So, RIA for this will be A, B, C, there are C signals. So, 3 outputs, A output, B output, C output, very simple. So, your A output is what in general A I comma j comma k, the coordinate is I comma j comma k, a general point, and going out is I comma j comma k, that will be A I j minus 1, because A is coming in the j direction. See the direction of A, that is the j direction, na, j axis. A is going in the j axis. So, A is coming from I remains I, k remains k, but only j changes. A is in this direction, this is my definition of j, j is in this direction, like xyz coordinate, this y coordinate, this x coordinate, z coordinate, instead of xyz I am calling ijk. So, A is in the j direction. So, as if this coordinate is called I comma j comma k, and the signal that is coming out in the output form, standard form, this signal I will call A within bracket I comma j comma k. That is what? Same as what is coming from here. So, what is coming from here? Previous node. What is that? I remains I, k remains k, but j becomes only j minus 1, isn't it? That is what it is. Similarly, B is in the opposite direction. B I comma j comma k, B is in the I direction. It will be B I becomes I minus 1, j and k remain same. And C, the one that comes up, C I comma j comma k will be C what? I j k minus 1, very good, plus these two things, these two multiplication, MAC after all, there is a computation done. But after writing these two, I can substitute this for this and this for this. So, I basically write using step jump. Okay. So, this gives rise to again RDG of this kind of form, A, B, C. What is this H? I to I means 0, k to k 0, but j minus 1 to j 1. So, this is a 3-dimensional edge like this, and this is I minus 1 to I, so 1 and then 0 0, and this is 0 0 1, I remains I, j remains j, but k minus 1 goes to k transpose, and here ijk, 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 ijk. So, 0 0 0, absolutely same. Now, you introduce affine scheduling and all those things, that I will consider after we meet. Okay. So, I will take down these 2 pages, so that I do not need to redraw them, so I have to quickly complete this history chapter. Okay. Thank you very much.